This is the quiz review video for our first magnetism quiz. First, some 4 facts you need to know. Rules for magnetic fields are the same as electric field lines. For example, line spacing indicates strength. If you don't remember all the rules for electric field lines, you might want to go back and look those up because they are the same for magnetic fields. Magnetic field lines point from the north end of a magnet to the south end of a magnet. They also point the way the north end of a magnet would go. So just like electric field lines point the way a positive charge would go, magnetic field lines point the way the north end of a compass would point. And so a compass's north end will point the direction a magnetic field line points. Finally, number 4, something that people have been messing up as they've been talking and have been getting confused about. A field can cause a force, but a field is not the same thing as a force. So remember, an electric force can be caused by an electric field when a charge is placed in it, but you wouldn't ever talk about like a field pushing a charge. The force caused by the field can push a charge. And that becomes important when we're starting to talk about magnetic and electric forces balancing each other. I heard some people on Friday talk about the electric field needs to balance the magnetic force, and that's not correct. An electric force might balance a magnetic force. An electric field, though, would never balance a magnetic field because there's nothing to balance. The fields can cause forces, but they are themselves not forces. And that's particularly important with magnetic fields because magnetic fields don't ever cause forces that go in the same direction they do. And so you can get really confused. Like if you're trying to say which direction is the magnetic field, to cause a force, let's say, upward on a charged particle. So if I want a magnetic force upward, I would certainly not have a magnetic field pointing upward because the force is caused by the right-hand rule, and the field can't be pointing upward to make a force upward. Okay, so it's really important to remember that fields can cause forces, electric and magnetic fields can cause forces, but the electric and magnetic field is not the force. And it also has tripped people up in the past. If a question asks for the strength of a field, make sure you're solving for the strength of the field, in this case E, or if we were looking at a magnetic force, QV cross B, you'd be looking for B. If the question asks for the force, that's when you're looking for the F. And in the free body diagrams, it's the forces that would matter. So if you've got a particle in equilibrium between a magnetic force and an electric force, make sure if you're answering questions there, you're actually talking about the force, because it can be confusing. For example, if we want an electric force to the left on an electron, we would need an electric field to the right to make that force to the left on an electron, because electrons get forces opposite the direction of electric fields. So the distinction between electric field, electric force, magnetic field, magnetic force really needs to be clear in your mind. So take a moment to think about that and look through your notes again if you don't feel like that's clear in your mind. Remember that to determine the force from a magnetic field, so let's say we have a magnetic field to the right, and we want to determine the direction of that force caused by a magnetic field on a moving charged particle. We refer to the equation force vector equals Q velocity vector crossed with the magnetic field vector. Well, if I just put a positive charge right here, it will not experience a force from that magnetic field because as I've drawn it, there is no velocity. And so if there's no velocity, there is no force. But if I gave that charge a velocity upward, then check it with me. We do the right-hand rule, velocity up, magnetic field to the right. I get that the magnetic force would be into the page. So I need to switch colors since my velocity was red. I get that my magnetic force would be into the page. Up, cross right, gives me in. Then if I wanted to know the amount of force that charged particle is getting on it, I'd go to the magnitude of the magnetic force is QVB and the sine of the angle between V and B. And here, if they're perfectly perpendicular, the sine is 90, and sine of theta just becomes 1. So it reduces to QVB if your magnetic field and velocity are perfectly perpendicular. So the equation is as simple as QVB if you know for sure that the direction of the charged particle and the magnetic field lines are indeed perpendicular. Now, it's clear B is not the magnetic force. So again, keep straight that distinction, field and force. Now, if we wanted to maintain the velocity of that charged particle going straight, so if we didn't want it to experience the force into the page and thus curve more back that way, imagine that going back into the page. Because, you know, a magnetic field will try to make a charged particle go in a circle. And by the way, that would mean that if that charged particle were to start traveling in a circle, the magnetic force would be the centripetal force, and then we could say equals mv squared over r. And then we could ask questions about that. For example, if I asked you, if I double the velocity, how much does the radius change? You would need to first, by the way, solve for radius. You couldn't answer that question the way the equation is written now without getting really confused. So you need to make that equation say r equals something. So we take this and turn it into r equals. Then plug in the change I've described for the velocity, and that's particularly important because there's two velocities. If I asked you how much the velocity would change if the radius was cut in half, we'd have to solve for radius. Sorry, we'd have to solve for velocity, and then plug in our change for the radius. If I asked you how much the radius would change if the mass were changed, you have to solve for the radius and then plug in your mass. So if you're asked about change problems with that equation, make sure you actually solve for whatever it asks about before you start plugging in your changes. But my point there was, if we wanted to cause that particle to not go in a circle and keep its velocity straight, we need to add in an electric field. Consider for a second, if the magnetic force is into the page, and this is a charged particle, positively charged particle, which way would we need an electric field to point to balance out or keep that charged particle at equilibrium? So we'd want it to be in translational equilibrium, moving with balanced forces. Since it's a charged particle, since the magnetic force points in, we need an electric force, so electric force pointing out of the page. And so this is a charged particle, positively charged particle, I keep doing that, positively charged particle. It would travel in the same direction, get a force in the same direction as the electric field, so we need an electric field out of the page. Now if this were an electron, the electric field would have to go opposite the way we want the electric force to be, which is something that people got confused about trying to remember on Friday. So remember that electrons will get forces opposite electric fields. Protons will get forces in the same direction as the electric field. And I should be even more general. A negative charge can be something other than just one electron. A negative charge will get a force opposite the electric field direction, and a positive charge will get a force in the same direction as the electric field direction. One thing I've done a poor job, I think, of talking about is the units for magnetic fields. So magnetic field strength, so if we're looking just at the strength of the field, is measured in Teslas, named after Nikolai Tesla, and usually represented with T, so Tesla is the unit for magnetic field. And since I also often ask you other ways to express units, a Tesla is also a volt-second per meter squared, a Newton per amp meter. Haven't done Weber's, we'll leave that one out. It's also a kilogram per Coulomb second. They use negative ones there to indicate the fractions. It's also a kilogram per amp second squared. It's also a Newton second per Coulomb meter. All of those things are equivalent to a Tesla. Take a second, consider that. Make a note of that. And you could solve for that by thinking about QVB equals mv squared over r. So if you really couldn't remember, you could plug all that in and then reduce it into whatever units you could remember. You'd eventually get charge per second, which on the bottom, which would be amps times meters over newtons, or newtons over amp meters. So easy one to arrive at from the fact that magnetic force is often centripetal force. Wonder why I talked about that. Could be important. Last thing I would say is practice some multiplication in scientific notation. So let's say I gave you 5 times 10 to the negative 19th times 6 times 10 to the 5th. Try it real fast in your head. Maybe pause the video. Okay, and you should have gotten 30 times 10 to the negative 14th, or 3.0 times 10 to the negative 13th. Okay, just going to know that you're going to have to do some multiplication with scientific notation without a calculator on Monday. Be ready for that. And that's all. Good luck.